Good afternoon, dear friends. Um, Today we are starting the part 3 comparative static analysis with the chapter 6 comparative statics and the concept of derivative in our book by Chiang and Kevin Wainwright, Alpha Chiang and Kevin Wainwright. So, as the name indicates, we will be comparing two equilibrium situations, two equilibrium positions, the initial equilibrium and the final equilibrium. So the first subtitle is 6.1, the nature of comparative statics. Statics, because we are comparing equilibrium situations, because we don't make a dynamic analysis, because we don't study the passage from one equilibrium to the other one, but compare the two static equilibrium positions. That's why it is statics and comparative statics, because we try to understand the change by comparing its initial position and its final position without taking into account what happens between the two, how one passes from the initial equilibrium to the final equilibrium. So this is our topic. When we are in an initial equilibrium position, one or some of the exogenous variables or parameters may change, and as a result of this change, the initial equilibrium is destroyed, and if it exists and it is possible to reach it, a new equilibrium is established. So, for instance, here you see there is P0 star, Q0 star, which is the equilibrium position of price and quantity in a market, the initial equilibrium. And then the tastes of the consumer changes, for instance. Then we obtain a new equilibrium. We reach a new equilibrium, P1 star, Q1 star, which can be, the final price, the equilibrium price, can be higher or lower than the initial equilibrium price. 0 means initial, 1 means final. Star means equilibrium or solution. We can also use the small case letter E for equilibrium, as one encounters in the economics books. And P is price. Q is quantity demanded, equilibrium quantity of a market where the supply and demand are equated. And it passes from Q0 to Q1, Q0 star to Q1 star. Star or E means equilibrium situation. So this Q is not any Q, but Q0 is the initial equilibrium position of the value of the quantity of a good, and Q1 star is the final position of equilibrium of this, the quantity of this good. You see, in a macro model, for instance, we can have Y0 star, C0 star as the initial equilibrium, and Y1 star, C1 star as the final equilibrium. 0 is initial, 1 is final. It stands for final. Star for equilibrium, and Y, the big case Y, as you know, is the national income, and C is the aggregate consumption of a society. So we can obtain an initial equilibrium position as Y0 star, C0 star, and the final equilibrium, the new equilibrium, can be formed at Y1 star, C1 star levels, you see. So the question is this: how can one compare the new equilibrium with the old one? In the comparative static analysis, the passage between the two equilibria is not analyzed, only the initial and final equilibria are compared, as I said. The analysis can be quantitative or qualitative. This is important because in the qualitative analysis, what counts is only the direction of the change, the sense of the change, not the quantity, the measure of the change. So if the direction of the change is studied only, this is qualitative analysis. If the quantity of the change is studied as well, meaning the level, the measure, if you have a measure in units, for instance, of a change is studied as well, then this becomes quantitative analysis. And the quantitative analysis includes the qualitative analysis as well. Not only the quality, but the quantity measure is included as well. So the quantitative analysis includes the qualitative analysis as well. And the inverse is not true. The ratio of a change in an endogenous variable to a change in an exogenous variable or parameter is called rate of change. Rate of change of y with respect to x, for instance. This is a rough measure. We will call it delta y or delta x, for instance, in a rough countable or measurable in rough quantities, rough levels. But if this ratio is measured in a very neat, sensitive way, taking the limit of this rate of change, then we obtain the derivative of y, for instance, with respect to x. And the related branch of mathematics, which we are starting now, is called differential calculus. What we are dealing now, what we are starting to deal with, is called in mathematics differential calculus. This is the branch of mathematics dealing with these infinitesimal changes, very small changes. So, 6.2, we are at 6.2, the rate of change and the derivative. We have a primitive function, y equals f of x. This is called primitive function because all starts by this. So this is the function modeling the behavior of the model. Y equals fx or f of x. So y is an endogenous variable and x is an exogenous variable or parameter. The difference quotient or rate of change or rate of variation all mean the same thing. Those are the three different names for the same measure, same concept. We will learn it. So we start by the difference or change. We show it with the Greek uppercase letter delta. This is delta, you see, as a triangle. This is delta, and delta x is defined as x1 minus x0, which is the final position of x minus the initial position of x. The final quantity minus the initial quantity of x. So this is delta x. Delta y is defined as y1 minus y0, meaning the final quantity of y minus the initial quantity of y, the final measure of y minus the initial measure of y. So those are the differences. They are called delta, and in everyday language, they are called difference or change, delta. Delta is the letter D in the Greek alphabet. So this is a kind of D, like difference. It comes from there. So y equals fx. What is it? 5 minus x squared. This is an example. We have a function, y equals fx, which we read as 5 plus x squared. Great. At the initial position, for instance, we have x0, which is 0. And at the final position, we have x1, which is 2. So the x, the variable x or the parameter x, augments from 0 to 2. It changes. What is the change in x when x goes from x0 to x1? x1 is x0 plus delta x. If delta x is x1 minus x0, then x1, just adding plus x0 to both sides of this equation, or this equality. In fact, this is an identity more than an equality. It's a definition. But if we add plus x0 to both sides, we obtain x1 equals delta x0 plus delta x. So the final position of x is equal to the initial position of x plus some change, the delta x. And y0 is fx0, the initial position of y, which is a function, the function f of the initial position of x0. And y1 is the final position of y, which is the function of x1, which is the final position of x. You see, just replacing the final position of x1 in the function f, we obtain the final position of y, which is y1. And this is equal to, of course, f of x0 plus delta x. Why? Because x1 is equal to x0 plus delta x. So here we have the elements. So if x changes from 0 to 2, x0 is 0 and x1 is 2. What is y0? Y0 is f0, f of 0, which is 5 minus 0 square. 0 square is 0, 5 plus 0 is 5. And f2, instead of x, we replace 2 in the function. 5 plus x square, 5 plus 2 square it would be. Then we obtain 2 square is 4, 5 plus 4 is 9. So when x goes from 0 to 2, y changes from 5 to 9, you see? So the difference quotient is the average change in y as a response to a 1 unit change in x, in relation with x0 and delta x, of course. The initial position of x, x0, and the change in x, which is delta x. You see, we have the formula here as well. All right, for instance, here, when x changes from 0 to 2, x0 is 0, x1 is 2, so delta x is 2 minus 0, 2. y0 is 5, y1 is 9, so delta y, which is y1 minus y0, is 9 minus 5, which is 4, you see? And if we divide this 4 by 2, we obtain this delta y over delta x, which is the rate of change or difference quotient or rate of variation of y with respect to x, you see? And which we can denote as delta y over delta x. Delta y is the change in y or difference in y, and delta x is the difference or the change in x. So we take an average. We divide delta y by delta x so that we obtain the average change in y in response to a 1 unit change in x. You see? And if we put these quantities in, if we open this formula, we obtain this. At the denominator, we have delta x, the change in x. At the numerator, we have f of x1, which is y1, minus y0, which is f of x1 minus f of x0. And x1, since x1 is x0 plus delta x, we can write it down as f of x0 plus delta x minus fx0 over delta x. You see? F of x0 plus delta x minus f of x0 over delta x. This is a more open form of delta y over delta x, which is the difference quotient or rate of change or rate of variation. You can use any of these expressions. They mean the same thing. It's delta y over delta x. Let's make an example and understand a little bit better. So y equals f of x is 3x squared minus 4. We have a function like this. This is our primitive function. Let's form the f of x0 and f of x0 plus delta x, which is f of x1. x0 plus delta x is x1, don't forget it. F of x0 is y0, f of x1 is y1. So we will obtain these and then form the delta y over delta x, which is the rate of change, or rate of variation, or difference quotient, as you wish. So f of x0, instead of x in the function, we replace x0. So 3 times x0 squared minus 4. Great. F of x0 plus delta x is at that time we replace x by x0 plus delta x in the function. So 3 times x0 plus delta x squared, the whole in square, minus 4. So, and what is delta y over delta x? Well, this is not so difficult. At the denominator, we have delta x anyway. And at the numerator, we have y1 minus y0. This is delta y, which is f of x0 plus delta x minus f of x0, which is 3 times x0 plus delta x in square minus 4 minus 3 times x0 square minus 4. So, if we develop this expression, we obtain here x0 square plus 2 times x0 delta x plus delta x square multiplied by 2, we obtain 3x0 square plus 6x0 delta x plus 3 delta x square. And here we have minus 4 minus 3x0 square, just distributing this minus 1 into the parentheses, we obtain minus 3x square plus 4. minus 4 and plus 4 annihilate each other. It's 0. It goes away. And then we have 3x0 squared minus 3x0 squared, which go away as well. They annihilate each other. So we remain with 6 times x0 plus delta, x0 times delta x, plus 3 times delta x squared, all divided by delta x. And since delta x is not 0, however small it might be, it's not different. It's different from 0. It can be negative or positive, but it's not 0. So we can simplify. We simplify these delta x's and we obtain 6x0 plus 3 times delta x. Here we have delta x squared. It's 1 is clarified with 1 delta x at the denominator. We remain with 3 delta x, you see. So the whole, all in all, the delta y over delta x is equal to 6x0 plus 3 delta x, you see. So this is the expression of the rate of change or rate of variation or difference quotient. So we obtain an expression at the value of x0 of the initial. Just we put the initial value of x as x0, and delta x is the change from the initial to the final value, which is whatever. Here in an example, for instance, we have x0, which is 3, and delta x is 4, which means x1 is 3 plus 4, 7. X changes from 3 to 7. So delta x is 7 minus 3 is 4 delta x. And x0, the initial level is 3. x1 is 7, of course. 3 plus 4, you see. And the delta y over delta x. Sorry for this, the position of these expressions. At the PowerPoint presentation, they are correct. But when I transfer the PowerPoint presentation to this software here, to this program, it shifts a little bit these expressions, these lines, so that we obtain a little bit sort of a mixed up or a little bit not so well aligned expressions. But at the PowerPoint presentation, they are correct. Huh? All right, so x goes from 3 to 7. x0 is 3, delta x is 4. So delta y over delta x is 6 times x0 plus 3 times delta x, which is 6 times 3 plus 3 times 4, which is 18 plus 12, 30. Which means when x changes from 3 to 7, for each unit of change in x in average, y changes 30 units of itself. X is measured by its own units, and y is measured by its own units. They don't have to be equal, these units. One is kilograms, the other one is meter, for instance, or one is kilowatt hour, the other one is, I don't know, the kilogram force, for instance. It depends on what we measure. So those are, they are not unitless. All have units. All these quantities, x's, y's, have units in according to their own nature, whatever it is. If it is energy of electricity, for instance, then it is kilowatt hours, for instance. If it is apples, kilograms. If it is, I don't know, something which we measure in meters, then it is meters or centimeters. You see, everything has its own unit. Then afterwards, we will learn how to save these expressions from units afterwards. All right. So the derivative. So what is the derivative? The famous derivative. Well, it is when delta x goes to 0, which means when it becomes very small. Delta x goes to 0, as you see here, delta x goes to 0. It means delta x, the change in x becomes very tiny, very small. X, the difference between x0 and x1, the distance between x0 and x1 is getting closer and closer, smaller and smaller. x1 approaches to x0, or delta x approaches to 0. This is also a way of saying the same thing. So delta y over delta x, where does it approach? Where does it go? If delta y over delta x in our example is 6x0 plus 3 delta x, and if delta x goes to 0, it diminishes, it doesn't become equal to 0. It never becomes equal to 0, but it goes very close to 0. So delta x goes to 0, so 3 times delta x will go to 0 as well. And the whole expression, this 6x0 plus 3 delta x will go to 6x0. This is the derivative of this expression, this function f, which we have in hand, at the point x0. So as a definition, it is the limit of delta y over delta x while delta x goes to 0, which is the limit of the rate of change of the function when delta x, the change in x, goes to 0, when it diminishes very much. It is a limit. Limit while delta x goes to 0 of, for instance, in this expression, 6x0 plus delta x, 3 delta x I mean, when delta x goes to 0, 3 delta x goes to 0 as well. So we remain with 6x0, which is a constant, 6 times x0, whatever the value of x0. So this is, in fact, the derivative value, the value of the derivative of this function at the point x0. It is called the derivative of y with respect to x. It can be shown by dy over dx. This is Leibniz, the famous German mathematician Leibniz definition or the notation, or f prime x, which is Lagrange, the famous French mathematician, Lagrange's definition, f prime x. dy over dx is equal to f prime x, and by definition it is equal to limit of delta y over delta x when delta x goes to 0. Limit of the rate of change when the change in x goes to 0. You see, this is the derivative. Y equals fx is called, f of x is called a primitive function. Why primitive? Because I mean, everything starts by this function. That's why primitive. It doesn't mean a caveman or something. It is just the starting function. That's why a primitive function. And when we take this derivative of this function, dy over dx, or f prime of x, then we call it derivative function. The primitive function is a function and the derivative is a function too. You see? For instance, let's see this example 2. Y equals fx equals 3x to the power 2 plus 4. A little bit different from the previous one. There it was minus 4, I guess, but it doesn't change. It's a quadratic function, a second degree function, a polynomial. All right, so y equals fx equals 3x to the power 2 plus 4. Great. F of x0, f prime of x0. F prime of x0 is 6x0. It is the same. If we replace the same, well, let's return to the formula here. You see, here it was minus 4, but there in this the other example is plus 4. It doesn't change anything because the plus 4 and the minus 4 here, or the minus 4 and the plus 4 here, they annihilate each other. These 4s don't count at all. What counts is the 3 times x to the power x squared. So, and the only change which occurs if we take 3x to the power 2 minus 4, well, plus 4 instead of minus 4, is we obtain 6x0 plus, no, but here we obtain minus 3 delta x. But when delta x goes to 0, 3 delta x will go to 0 as well, so we will remain with 6x0 anyway. You see? So, f prime x0, f prime of x0, which is the derivative function of f of x at the point x0, is 6x0. The value of the derivative at the point x0, it means. If we replace x0 by any x, then we obtain the derivative function of y with respect to x in terms of x, which is dy over dx, which is equal to f prime x, and which is equal to 6x. This is the derivative function of this primitive function, 3x to the square plus 4, you see. All right. For specific values of x, x0, then we should replace x by this special value of x0. What can it be? For instance, if x is 3, then we put 3 here. 6 times 3 is 18. This is a specific value of the derivative. The derivative itself is a function, And this is the value of this derivative at the point x0 equals 3. But if x is 4, for instance, x0 is 4, then we put 4 instead of 3, instead of x0. So we obtain f prime of 4, which is 6 times 4, which is 24, you see. So the value of the derivative changes as well. Here there are some exercises, you just try them, and there are solutions at the back of the of your book and in the solution book, the teacher's book, which I shared with you, which I sent you. You find it at our web page, at the page of our course. All right. So we are at 6.3, the derivative and the slope of a curve. So the geometric meaning of the derivative. We are now, we will be studying the geometric and also the economic meaning of the derivative. Here in our book, it is done with an example. We take a total cost function. Here, actually, you can, in any mathematics book, you will see y equals f of x, this function. And at the horizontal axis, you will see x's, and on the vertical axis, you will see y's. So we will obtain y equals f of x and delta y over delta x, or dy over dx is as rate of change and the derivatives. But here, the book preferred to, or the authors preferred to tell the same story with an economic example. The total cost function, which is the cost of producing or selling something, which is C equals f of q. This is a total cost function in terms of the quantity produced or quantity sold of a good. You see, C equals f of q. This is the total cost function. Q is the quantity of output, whatever we produce or sell. Marginal cost, perhaps you have heard about it. Marginal cost is denoted by MCQ, which is the marginal cost in terms of the quantity. It is equal to delta C over delta Q, which means the rate of change of the total cost with respect to quantity produced or quantity sold. This is a rough measure. This rate of change is a rough measure, a finite measure. Delta C and delta Q, we can measure it by kilograms, for instance, and delta C by liras. And they are rough measures. They are not very neat, very sort of sensitive measures. But if we send delta Q to 0, if delta Q goes to 0, which means here the denominator is becoming smaller and smaller, then marginal costs of the quantity, marginal cost with respect to quantity, will be the limit of the delta C over delta Q when delta Q goes to 0, which is equal to the derivative of total cost with respect to Q, with respect to the quantity. So dC over dQ is the derivative of total cost with respect to quantity, which we call in economics marginal cost of Q. You see, this is the marginal cost. This is a neat, very thin, very neat, very infinitesimal measure. It's almost theoretical. It's in our head. Delta C and delta Q, we can measure it. dC and dQ, we can't measure it really. They are concepts, but they serve. And dC over dQ, this derivative, we can measure it at any point at the function. So this is a neat infinitesimal measure. What does it mean? It means the change caused in the total cost by 1 unit of change in the output, in average, dC over dQ. And at the very near the point of start, the point of the initial equilibrium. Here we see the initial equilibrium on this graph taken from the book. It's the figure 6.1 in our book. We have Q0 and C0. The point A is the initial equilibrium point, whose abscissa is Q0 and whose ordinate is C0. Q0, C0, this point A, whose coordinates are Q0 and C0, is the initial equilibrium. The point B is the final equilibrium, and here the coordinates have been put as Q2 and C2. Why not Q1 and C1? Because Q1 and C1 we will use for an interim sort of position. That's why. All right. So what is delta C over delta Q and dC over dQ? If we just consider this picture now, this diagram. This is the drawing of the function. C equals f of Q is this thick line. This is the function C over equals f of Q. This is the primitive function with thick line. It is a function of Q of C with respect to Q. So the total cost is measured well, in liras, and it is a function of the independent variable, which is the quantity produced or sold, which is Q. So C equals FQ, f of Q, this function, the total cost function. When we start by the initial position, initial equilibrium Q0, C0, which is the point A, and we have a change in Q, which is denoted by delta Q. The Q goes from Q0 to Q2. There is a change in the quantity produced. We produce a little bit more of Q, whatever it is. We produce a little bit more apples, for instance. Then our level of production rises from Q0 to Q2. Great. And this is the difference, Q2 minus Q0 is delta Q. This difference is here. And we can find it as well between the points A and E. Here we find the same distance, Q2 minus Q0, which is delta Q, you see. And when Q augments from Q0 to Q2, we have also the total cost which augments. Each unit of Q which we produce augments the total cost. There is no costless production, so it augments the total cost. And when we match Q2 with the function, we find C2 as the image of Q2, which is the total cost of producing quantity Q2. This is the point B. So if we join the point, the initial equilibrium A with the final equilibrium B, we obtain this chord. This portion of the function is called an arc, like the arc which old people used for like a bow, you know, to cast arrows, to throw arrows. You have a bow, which is an arc actually, and the string we use in order to give the force to the arrow is called a chord. This one. So this portion of line between A and B is called a chord, and its slope, the slope it makes with the horizontal line X or Q or whatever. Here we find the same horizontal line. It is the an angle alpha. Here we have an angle alpha, and the tangent of this angle is the opposite the opposite side by the neighbor side, by the adjacent side, which is BE or EB over AE, which shows the slope of AB, the slope of the line AB, of the hypotenuse. Here we have the hypotenuse or hypotenuse, and when we divide the opposite side by the adjacent side of this angle, we obtain the tangent of alpha, this angle alpha, which shows the slope of the line AB, alright, of the chord. So delta C or delta Q, this is delta C. You see, delta C is the change from C0 to C2, C2 minus C0. This is delta C. It is equal to EB. It's the same distance. And delta Q is equal to AE. It is the same, Q2 minus Q0. We find it here as well. So the tangent of the angle alpha here, of angle A, let's call it, is delta C over delta Q. This is the slope of this chord, which is well, which is a rough measure of the rate of variation. It is a rough measure of this slope. But if we diminish this quantity, instead of augmented Q0 to Q2, let's augment it to Q1, for instance, a smaller distance. Delta Q gets smaller. Then we obtain as an image the point D on the function and C1 as a cost of this producing Q1. C1, Q1 is the point D. There is again a chord from A to D, from the initial equilibrium to the final equilibrium, which has come nearer to the initial equilibrium now, and we have an angle here, and its opposite side to adjacent side, the chord being the hypotenuse. It is the tangent of the angle A, which is the slope of this chord, but now it is smaller, you see. And if we continue sort of making delta Q smaller and smaller, at the end, this B approaches A very much, and at the end it becomes almost 1 point, and the chord becomes the tangent line passing by the point A. This tangent line, you see in blue. So if we measure here, we have this actually the measure of this. The if you wish, here it doesn't show very well because the the slope has changed a little bit. But if we again, here there's a triangle with a right angle, and if we divide the opposite side by the adjacent side, we obtain the slope of this tangent line, which is the derivative. This time, this is the derivative. When we measure the slope of the chord between A and B, it is the rate of change. But when the difference delta Q goes to 0, this chord becomes the tangent line, passing only by A, touching to A and continuing. This is tangent, which touches at 1 point and continues. So when we take the slope of this line, it is the derivative, dc over dq, the derivative of the cost function with respect to the quantity, which we call also marginal cost. So in economics, marginal cost can be both the rate of change of the cost with respect to the quantity if we measure it roughly with a finite measure. If we measure it very neat, very thin, very sort of infinitesimal, then it becomes the derivative. So in economics, marginal, we use the concept of marginal for both the rate of change or the derivative. If we measure it rough, it is rate of change. If we measure it very neat, then it is the derivative, you see. All right. So the concept of limit. Now we have to understand what the limit is, which is not always so easy. All right. 6.4. We are at 6.4 now. The concept of limit. Here, in mathematics books, it is it is told with x's and y's. But here in our book, it changes some variables. It calls v for delta x and q for delta y over delta x. Q is quotient because this is a quotient of differences, delta y over delta x. And v variation, v is the initial of variation for delta x variation in x, change in x or difference in x. You see, this is v. So instead of v, you can put x, and instead of q, you can put y if you wish, and you obtain all the same, the same sort of story and the same formula in the mathematics book. It is the same. Here, our book prefers to tell the story by v and by q because it wants to end up with the derivative rather. That's why. So dy over dx is, as we said, it is by definition limit delta y over delta x when delta x goes to 0. If delta y over delta x is q, and delta x is v, then it is the limit of q when v goes to 0. You see? We can also replace these variables by equivalent symbols. So, but what is limit of q when v goes to 0? One important sort of remark I should make is that if a variable goes to somewhere, it doesn't mean it is equal to that. In fact, it doesn't mean that it is equal. It's not equal. It is never equal, but approaches very much this point. It never touches this point. You approach, you come closer to a hole, but you never fall in the hole. You come closer to a wall, but you never touch the wall already. You see? So let's start by left side limit and right side limit, because the limit of a function at a point is it exists when the left side limit is equal to the right side limit. So we should first learn the left side limit and right side limit, and then when these two quantities or two limits are equal, then we say that the function has a limit there, and it is the value L, which is the equal value for left side limit and right side limit. So what does it mean? The question is this: when a variable goes towards or approaches another variable, go toward or approach is the same thing. When a variable goes towards or approaches another variable, towards which value goes or approaches the other variable? The answer to this question is the limit. So q is equal to g of v. There is a function g tying v to q. Or you can tell the same story by y equals f of x. The same thing, no problem. If you wish, you can replace q by y and v by x and tell the same story, all these formula, all these things, the same for y equals f of x. You see? So if v goes to n, a value n which is a real number, n belongs to the real set of numbers, real numbers. So n is a real number, v, which is a real variable, goes to a specific value n, which is real. In this case, where does q go? Which value q approaches? This is the answer to this question is the limit of q when v goes to n, the big case letter n. So you can tell the same thing when x goes to x0, which is a real number, where goes y equals f of x. Where does it go? This is also the same thing. V can go to 0, for instance. Where does q go? X can go to 0, so where does y equals f of x go? You see, v can go to plus infinity or minus infinity. Then where does q go? X goes to plus infinity, where does y go? It's the same question. So the answer is the limit of y when x goes to plus infinity, or limit of q when v goes to plus infinity. It's the same thing. Attention, yes, this is an important remark. You should never forget this. Infinity is not a number, but a concept. It is not a number. You can't reach infinity. Nothing but limits can be equal to infinity. A number, a constant, an x cannot be equal to infinity. Only limits and concepts based on limits, like derivatives and other things we will learn, can be equal to infinity. Something which is not a limit itself cannot be equated to infinity. We never reach infinity. We just go towards infinity. All right. So here is an example. V goes to minus infinity. Where does q go? Or when x goes to minus infinity on a number line of numbers, from minus infinity to plus infinity. You start from 0, for instance, and you walk towards minus infinity. you diminish your numbers and you go towards minus infinity. You never reach it. X goes to minus infinity. X is not equal to minus infinity. X goes to minus infinity. This arrow means this. And y goes, where does y go when x goes to minus infinity? The answer is the limit of y when x goes to minus infinity. So when v goes to n from smaller values of n minus it is called. When v is less than n, but it goes to, it augments towards n. Then where does q go? To which L value does Q go? The answer is the left side limit of Q. L is the left side limit of Q, which is the limit of Q when V goes to n minus. N when V goes to n minus means V is smaller than n and it approaches n from values less than n. When V goes to n plus, which means V is greater than n and it approaches n from values greater than n. So where does Q go? Q goes to L. Then this L is the right side limit of Q. Limit of Q when V goes to n plus. V goes to n from higher values. Then it is limit of Q when V goes to n plus. This is the right limit. The limit of Q when V goes to n minus is the left limit. If these two limits are equal, it's the same L, left side limit or right side limit, if they are equal, or left limit or right limit. One uses more left side limit than right side limit. If both left side and right side limits of Q are equal, then this value L is called the limit of Q when V goes to n. So they should be equal and have a value, not to be infinity. Then plus or minus infinity, this L. So we can say this L is the limit of Q when V goes to n. Of course, the limit of Q when V goes to n can be plus infinity or minus infinity as well. The limit can be equal to plus or minus infinity. But then again, if it is equal to plus or minus infinity, or if right limit or left limit from the right and limit from the left are not equal, we say that the limit of Q does not exist. When V goes to Q to some value, for instance, to n, and the left side and right side limits of Q are different, or the one of these is zero, is infinity, limit of Q is plus infinity or minus infinity, then we say that the limit of Q does not exist when x goes or V goes to n. You see, this is how the limit may not exist. All right. So let's see the graphical illustrations and try to understand a little bit more this concept of limit. This is a bit difficult. I confess. This is perhaps the most difficult lesson of the whole term. We will come to that. So graphical illustrations. In here we have four drawings, four diagrams, four functions, different functions, and with limits. Here at the A, this is A, B, C, D, A, B, C, and D. The A, the uppermost and the leftmost figure, we have, you see, when we approach V from the to n, towards n from lower values, V goes to n minus. V is less than n, and Q, you see, the Q values, the function values, go to L from below. So Q goes to L minus as well. When V goes to n minus, that is when V approaches n from values below n, less than n, Q goes to L from below, from values less than L. This is L minus is called the left limit of V. When V goes to left limit of Q, it should be, not left limit of V. It is called left limit of Q. Here there is a mistake. I will correct it in the presentation. Left limit of Q when V goes to n minus. This is the left limit of Q. Then when V goes to n plus, which is from values higher than n, when V is greater than n, and it goes to n from above, from values higher than n, then when we follow the function values of these, then we see that it approaches L as well from above. So L plus, when V goes to n plus, Q goes to L plus as well. L plus is the right limit of Q. Well, here we have L minus and the other one is L plus, but it doesn't change because both are L. They go to the same value. So L minus equals L plus equals L. That means limit of Q when V goes to N is L. This L is the limit of Q when V goes to N. You see? Here at this the second picture, we have the function. The thick line is the function. And we can draw it without taking our hand from our pen from the paper. Again, like this one. So when V goes to n from values below n, when V goes to n minus, when V is less than n and it approaches n from below, then Q goes to L minus. This is the left limit of Q. When V goes to n plus, being V values greater than n, from above, from right hand side, you see, from plus infinity towards n if you wish, then Q goes to L minus again. So in any case, there is no value above L in this function. Everything is below L, so they go to L from below. So left side limit and left limit and right limit of Q is L minus. The minus and plus doesn't change very much here. Where does the function approaches L? It approaches to L in both sides. So L minus equal and x equal to L. So limit of Q when V goes to N is L again. If whatever, I mean, whether we go from below values below N or above N, the function values go to L from below. The same L, so this is the limit. All right. In the third function, this is a step function. Why is it called a step function? It makes like a step of a stair, actually. See? So in this function, these types of functions are called step functions. So the function consists of two parts. One part up to n is L1. It's a constant function having the value L1. When x or v passes n, it goes over n, then we have another value for the function, which is L2, which is a constant value. So it is the union of two constant functions, L1 and L2. And the line of divide is n. Here there is a mistake in the book. One of these points should be empty, because one origin, one n, cannot be associated to two different values of Q. Otherwise, it won't be a function. In order that relationship to be a function, one of these points should be empty. One can be black, the other one should be empty, should be a hole over there. Or it can be separated with a half moon. This is also a way of showing that it is empty over there. But here, drawn as it is, it's erroneous, it's mistaken. All right. So when V goes to n minus, which is V being less than n, from this side, from minus infinity to n towards n, the value of the function is L1 and it goes to L1. But when we go from plus infinity towards n, from values above n, then the value of the function is L2 and it goes to L2. L1 is different than L2. The left side limit is different than right side limit. So there is at this point, at point n, V going to n, there is no limit of the function. You see? V goes to n minus, Q goes to, well, here V goes to n minus, Q goes to L1. V goes to n plus, Q goes to L2, and L1 is not equal to L2. There is a sort of descaling here. There is it's like a step. So L1 is different from L2, When v goes to n, there is no limit q. You see, it is one of the cases where there is no limit. The other one is the fourth graph, which is an asymptotic one. What does it mean, asymptote? A line approaching another line without touching it. Asymptote is the geometric sort of counterpart of the limit. Here you see the function consists of two parts. This is a hyperbola, a quadratic hyperbola function, and we could have drawn, if it is 1 over x, for instance, we could have drawn it just symmetrically to the point origin 0, 0. But here the point of symmetry is nm. The abscissa of the point of symmetry between the two is n, and the ordinate is m. So we have two asymptotes, n and m, where this function approaches. So let's study this function a little bit. It's very interesting though. When v goes to n minus, meaning that v approaches n from values below n, lower than n, then this function goes towards minus infinity. You see, q goes to minus infinity. But when v goes to n plus, meaning that v approaches n from the values above n, higher than n, then the function goes to plus infinity. Is this a limit? Yes, this is a limit. That is it means the limit doesn't exist. It augments and augments. The function augments here towards plus infinity, and here it diminishes towards minus infinity. But where does the function go? For instance, when v goes to minus infinity, when v becomes smaller and smaller, when v goes to minus infinity, the function values go towards m. So limit of q when v goes to minus infinity is m. And when v goes to plus infinity, this is the direction, the function makes this movement. So it descends, it goes down towards m. So limit of q when v goes to plus infinity is m, you see. We don't say that, well, they are equal, then it is the same limit, because in one v goes to minus infinity, in the other direction v goes to plus infinity. It's not the same limit, although by chance the limit is the same, this m. But those are two different limits, so we don't say limit of q when v goes to minus infinity is the same as the limit of m when v goes to plus infinity. They are by chance equal. Their equality doesn't mean much for us. All right, you see, those are various cases where we find the existence and non-existence of limits. All right, so how do we evaluate the limits? We have to be able to evaluate limits as well. Here we have some examples. Example 1 is q equals g of v, which is equal to 2 plus v square. This is a simple function. What is the limit of q when v goes to 0? What does it mean, v goes to 0? It means v becomes less and less, smaller and smaller. 1 over 10, 1 over 100, 1 over 1000, 1 over 10,000, 1 over 1 million, etc. So it diminishes. In the left side limit, which is when v goes to 0 from negative side, it is the left side limit. For instance, v can start by minus 1. Then it becomes minus 1 over 10, minus 1 over 100, minus 1 over 1000, etc. So v goes to 0 from below, from negative numbers. So it goes to 0 minus. But where does v square go then? V square is the square of v. Square of minus 1 is 1. Square of 1 over 10 is 1 over 100. Square of minus 1, 1 over minus 1 over 10 is also 1 over 100. The square of minus 1 over 100 is 1 over 1000. The square of minus 1 over 1000 is 1 over 1 million. You see? And it becomes positive because the square is positive. Although v is negative, the square of v is positive. And it approaches to 0, it goes to 0 from positive values, from values above 0. So the left side limit of q when v goes to 0 which is 0 minus, is v square goes to 0 from above. So 2 plus v square go to 2 from above. It goes to 2 plus. You see? This is the way of saying it goes to 2, it approaches 2 from above, from values greater than 2. Alright. And what is the right side limit? In the right side limit, v goes to 0 from positive values, from values above 0. So from 1, 1 over 10, 1 over 100, 1 over 1000, etc. It goes to 0 from above, from positive side. Then where does v square go? Well, it goes sort of faster to 0 from the positive side. 1, square of 1 is 1, the square of 1 over 10 is 1 over 100, the square of 1 over 100 is 1 over 10,000, square of 1 over 1,000 is 1 over 1 million. So it goes to 0 from above, so from positive values. So v square go to 0 from positive values as well. So 2 plus v goes to 2 from positive values. From values greater than 2, it goes to 2 plus. So these limits are the same. 2 is important, not their plus is not important, but their 2 is important, their value. It is the same. So the limit of q when v goes to 0 is 2. So this is an important note as well. We should note that v can go to n, but v is not equal to n, of course. V goes to n does not mean that it's equal. It means it's not equal. It approaches, comes closer and closer and closer, but it never touches. It is never equal to n. And even n may be outside the domain of definition of the function. The value of the function of n may not be defined at all. We can have a hole there, but we can approach this hole from left and right hand side very close, and if the value is the same, the function has still a limit over there. It may not be defined at that point n, but still may have a limit. You see? So the example 2 is also important, is interesting. Q equals g of v is 1 minus v square over 1 minus v. What is the limit of q when v goes to 1? Alright. If we replace v by 1 in this function, we obtain 1 minus 1 over 1 minus 1. Which means 0 over 0, which is an indetermination. It's it's indefinite. 0, we don't know what it is. 0 over 0. It's not defined. It's not determined. But so when v is 1, the denominator of this function is 1 minus 1, 0. So the function is undefined anyway at n equals 1. N equals 1 doesn't belong to the domain of definition of this function. But do we say that v is equal to 1? No. We say v goes to 1. It approaches 1 without being equal to 1. But then we can make some simplifications. So when v goes to 1, 1 minus v square goes to 1, 1 minus v square goes to 0, and 1 minus v goes to 0 as well. So the whole thing goes to 0 over 0, and this is an indeterminacy. But v goes to 1 does not mean v is equal to 1, it means v is not equal to 1. So we can simplify the expression. Note that 1 minus v square is 1 minus v times 1 plus v, or 1 plus v times 1 minus v. And at the denominator we have 1 minus v. So we have 1 minus v square over 1 minus v, which is equal to 1 plus v times 1 minus v over 1 minus v. And if, as long as v is not equal to 1, we can simplify these 1 minus v's, and we remain with 1 plus v. So besides the point, with the very point v equals 1, in all the other points, this function is equal to 1 plus v, for v different from 1. Then we can take the limit of this function when v goes to 1 as the limit of q when 1 plus v goes to 1. Why? Because v goes to 1 doesn't mean that it's equal, it means it approaches very much. So we simplify here and we remain with the function q equals 1 plus v. And when v goes to 1, this expression goes to 2. 1 plus 1, 2. So limit of q when v goes to 1 is 2 in this case. It has a limit. You see. Another example. Let's see. Q equals G of V equals 2V plus 5 over V plus 1. What is the limit of Q when X, well, not X, but V, it should be, V goes to plus infinity? Well, interesting. When V goes to plus infinity, you see, 2 times V goes to plus infinity as well. Plus 5 as well. This doesn't mean anything. It is constant. So 2 times infinity plus 5, it goes to infinity plus infinity as well. Everything goes to plus infinity in this case. And V, when V goes to plus infinity, V plus 1 goes to plus infinity as well. So 2V plus 1, 5 over V plus 1 go to plus infinity over plus infinity, which is an indeterminacy as well. But we can transform the expression and get rid of this indeterminacy. How can we do it? We can note that 2V plus 5 can be written as 2V plus 2 plus 3. We divide 5 by, we just separate it in 2 and 3. So here 2V plus 5 is equal to 2V plus 2 plus 3. The whole divided by V plus 1. Great. What is 2V plus 2? It is 2 times V plus 1. And we have plus 3. The whole divided by V plus 1. Great. So what is Q, which is 2V plus 1, 5 over V plus 1? It is if V is different from minus 1, which is not, it goes to plus infinity anyway. So we can simplify this V plus 1 and V plus 1. So here we remain with 2, and here we remain with plus 3 over V plus 1. So the whole expression, the whole function is 2 plus 3 over V plus 1. Great, we have transformed the equation, the function. We haven't changed anything, we just transformed, noting that 2V plus 2 is 2 times V plus 1. All right. So this expression, where does it go when V goes to plus infinity? When V goes to plus infinity, V plus 1 goes to plus infinity. It augments and augments. But 3, the numerator, the denominator augments towards plus infinity. The numerator is constant, 3. So something constant over something which goes towards infinity. Where does it go? 3 over V plus 1, it goes to 0. It becomes smaller and smaller and goes to 0. 3 over V plus 1 goes to 0. So where does the whole expression, if this part 3 over V plus 1 goes to 0, 2 plus 3 over V plus 1 goes to 2 plus 0, which is 2. You see? So the limit of Q when V goes to plus infinity is 2. We have got rid of this indeterminacy by transforming the function. These are very frequent questions, of course. All right. Now we are at the formal view of the limit concept, or the neighborhood definition of the limit of the concept of limit. And this is perhaps the most abstract and difficult part of the lesson to understand. So you should be careful, you should read it and write down and try to understand. None of us has understood at the first glance when we were studying, when we were students like you. The topic was also, this part was also difficult for us. So nothing particular, nothing to fear from. You should just be patient and go over all these details and try to understand what it means. So let's start. First, let's start by the intervals. You have certainly heard of these intervals, which we denote by parentheses, the soft parentheses, the usual soft parentheses, or the square parentheses, or accolades. Accolades are these fashionable, nice parentheses. You see, this is called accolades, or brackets as well. They are called brackets. So parentheses, or soft brackets, soft parentheses, square parentheses or square brackets, and accolades, which are nice brackets or brackets. All right. So we have open intervals, closed intervals, and semi-open or semi-closed intervals, or semi-open or semi-closed intervals. What does it mean? Well, an interval is a two-sided inequality. Let's start by an open interval. The open interval AB, which is denoted by a soft parenthesis in both parts, A and B are the frontiers, are the limits, are the frontiers of the interval. When we put these soft parentheses, it means it is defined as the set of real numbers between A and B. X is greater than A and less than B. They cannot X cannot be equal to A or cannot be equal to B. The frontiers are not included. They are excluded. In this case, we call this interval an open interval and denote by soft parentheses. Soft parenthesis AB means the open interval AB, which is the set of x's between A and B, but A is not included and B is not included. This means this. All right. The closed interval AB, which is denoted by this squared parentheses, squared brackets AB, means A less than equal to X less than equal to B. So X is again between A and B, the numbers or the limits, the frontiers between A and B, but A and B, the frontiers are included at that time. This time the frontiers are included. A is less than or equal to. We allow X to be equal to A or to B. A is less than or equal to X and less than or equal to B. So this is the closed interval. Semi-open or semi-closed interval is we put square brackets at one side and the soft brackets, soft parentheses in the other side. So what does it mean? Soft at the A side and squared at the B side means the semi-interval AB, semi-open interval AB, means A is less than X is less than or equal to B. So we allow X to be equal to B but not to A. This lower limit, lower frontier of X of the set is not included, but the upper frontier B is included. X can be equal to B but cannot be equal to A. X is between A and B, all right. But A cannot be equal, or X cannot be equal to A, but X can be equal to B. So this is the semi-open or semi-closed interval AB. Open from the A side and closed from the B side. And the opposite, for instance, here we have, for instance, you see, it's the same 3, 5. There are some examples here. The semi-open interval 3, 5 means 3 open and 5 closed. Open from the side of 3 and closed from the side of 5. It means the set of all x's, real x's, such that 3 is less than x, less than or equal to 5. But we can also have the other way around. We can have the semi-closed interval 6 plus infinity. From the infinity sides, an interval cannot be closed, can never be closed, because we cannot reach infinity. X cannot be equal to infinity. It can go towards infinity. So the infinity is when there is infinity in an interval minus or plus infinity, this infinity side should be open always. But the sixth side, the side of the 6, this constant real number, can be closed. And here it is closed, meaning that x is greater than or equal to 6, but less than plus infinity. So this is the set of all x's, real x's, such that 6 is less than or equal to x, and which is greater than less than plus infinity. You see, these are the semi-open or semi-closed intervals. What is then a neighborhood? Neighborhood is a very important concept. So, well, we have x0, a definite value of x, a starting point, for instance, and a value L, which is a real number as well. Those are real values. X0 and L are real values. And we have also two very small, tiny, neat numbers, or concepts rather. delta and epsilon. Delta and epsilon are strictly greater than 0. They are strictly positive. We show it as delta, this small delta, small d in Greek letters, small Greek letter d, and small Greek letter e. Delta and epsilon, d and e in small cap Greek letters. These denote very small, tiny changes in variables, delta and e, delta and epsilon. They are called delta and epsilon. The big delta is a rough change. Small delta or d is a very tiny, very infinitesimal change, as well as epsilon, small epsilon. These are, they belong, or they are members of the set R++, meaning that they are positive real numbers, but cannot be 0 either. They are greater than 0. They are always real positive numbers. All right. What is the delta neighborhood of x0? It's pronounced like this. The delta is read like this. Delta neighborhood of x0. It is denoted also by a kind of interval, but we should be careful in using it. It is x0 delta, which is called an open ball in a higher level of mathematics. And it is, for the moment being, we will consider it, we will take it as the interval x0 minus delta, x0 plus delta. It is the open interval. The delta neighborhood of x0 is the open interval x0 minus delta, x0 plus delta. The frontiers x0 minus delta and x0 plus delta are not included. Everything between x0 minus delta and x0 plus delta. This is called, this interval, this open interval, is called the delta neighborhood of x0. You see, x0 minus delta less than x, less than x0 plus delta. We can also show it this way. All these are different ways of showing the same thing, the delta neighborhood of x0. What is the epsilon neighborhood of L? It can be shown by this kind of, well, cursive symbol L epsilon. Open ball L epsilon, it's called. But here, for the moment being, we will take it as the interval, the open interval, L minus epsilon, L plus epsilon, meaning that the set of all x's between L minus epsilon and L plus epsilon, the frontiers L minus epsilon and L plus epsilon not included. L minus epsilon less than x, less than L plus epsilon. This is the L epsilon neighborhood of L. And the delta neighborhood of x0 is x0 minus delta, x0 plus delta, this interval, open interval, meaning x0 minus delta less than x, less than x0 plus delta. All right, so here comes the important parts. What is the limit? Now I will give you the formal definition of the limit of a function when x or v goes to a definite value, a real number n. It can be as well infinity if you wish, but for the moment being we take a definite n. So when v goes to n, the limit of q equals gv, limit of this function, is the number L only if one-sided arrow, you see, only if these conditions are fulfilled. If these conditions are fulfilled, the limit is this one, L. So when I repeat, when v goes to n, the limit of q equals gv of this function is the number L only if for any chosen epsilon neighborhood of L, however small it may be, and sometimes however big it may be as well, but in this case it's however small it may be, there must be a delta neighborhood of n in the domain of definition of the function, so that the function value of any point v in the delta neighborhood of n, besides n itself, n may or may not belong to the domain of definition. This the function value of any point v in the delta neighborhood of n should be in the epsilon neighborhood of L. This is the formal definition of limit in mathematics. I repeat, when v goes to n, the limit of q equals gv, you can take y equals fx if you wish, the same thing, is the number L only if for any chosen epsilon neighborhood of L, however small it may be, there must be a delta neighborhood of n in the domain of definition of the function, so that the function value of any point v in the delta neighborhood of n, besides n itself, n may or may not belong to the domain of definition of the function, should be in the epsilon neighborhood of L. Now, if you haven't understood anything, it's very normal. When we read or when we saw this definition on the blackboard in our university times, in our license, when making the license, the undergraduate studies, we haven't understood anything either. We were just like you. Don't fear. Don't get afraid. You will understand. So, what does it mean? What does it mean? All that sort of that complicated, complex set of words, which doesn't seem to mean anything for the moment. Of course, they mean. They have a very important meaning. Of course, I will explain you now. In our book, for some reason, the authors, they take asymmetric intervals. It's not necessary. We can just take L plus epsilon, L minus epsilon, the interval L minus epsilon, L plus epsilon, and N minus delta, N plus delta. In the mathematics books, it's always symmetric. They prefer N minus A or something, what is it? L minus A, L plus B, or L minus A1, L plus A2, and N minus B1, N plus B2. But it doesn't serve to anything, it just complicates the thing even more. The definition itself is complicated. When you try to define it with asymmetric intervals, it becomes even more complicated. It's not necessary. I will tell you in N minus delta, N plus delta, and L minus epsilon, L plus epsilon. Just imagine we are making an exercise. We are making a sort of experiment. We have a camera. Instead of camera, we can use our hands, and we form a, well, we have a, how can I say? We make a zoom. You know, the zooming in a camera. But this zooming, we don't make it in a circle. We make it in a square or in a quadrangle, a quadratic form, a quadratic frame. You see here we have a quadratic frame. Here in these pictures we have quadratic frames. So this quadratic frame is important. Why? Because the vertical distance of this quadratic frame is L minus 1, L plus 1. It is the neighborhood L minus 1, L plus 1. It is the interval, the open interval L minus 1, L plus, L minus epsilon, L plus epsilon, I mean. L minus epsilon is L plus epsilon, which is the epsilon neighborhood of L. This is this distance, the epsilon neighborhood of L. L minus epsilon, the interval L minus epsilon, L plus epsilon, which has a distance of 2 epsilon, of course. Then the horizontal side of this zoom, this quadratic sort of zoom, this quadratic frame, this part is N minus delta, N plus delta. So what the definition says that if I diminish this frame vertically, if I choose epsilon, less and less, smaller and smaller positive numbers, then I diminish the vertical distance L minus epsilon, L plus epsilon. For each epsilon, however small I choose this distance, I choose epsilon, therefore I choose this distance, then I should be able to diminish as well the distance n minus delta and plus delta. You see this horizontal distance. And while doing this, the function, the values of the function are always, they remain always in this quadratic zoom, quadratic frame. They don't go out of this frame. Then we say that when we go to n, which is the center of this neighborhood n minus delta and plus delta, the delta neighborhood of n, the function, values of the function, values of x's, values of v's, function values, remain in the epsilon neighborhood of L. L minus epsilon, L plus epsilon, the interval L minus epsilon, L plus epsilon here. If this is true always, then we say that the limit of this function q equals gv or y equals fx when x goes to n, when x goes to v goes to n, is the value L. L is the limit of the function when v goes to n. So let's see these examples here. In the first, you see, these are the examples we have seen above. The examples where the first two are with limit, the second two are without limit. There is also the step function and the hyperbolic function, the quadratic hyperbola. All right. So in the first one, you see, the function is very continuous. I can draw it without taking my pen from the paper. So if I form this quadratic frame and zoom towards the center, towards the point NL, we have the point NL at the center. If I zoom in, the function remains always in the portion of the function around n remains always in the frame. I can choose epsilon as small as I wish, meaning that I can diminish the vertical distance. Then, as a response, I will diminish also the delta distance, the horizontal distance, and diminish this square, or well, it can be square or it can be quadratic, whatever, this frame. Then, always the points around NL remain in this quadratic frame. They don't go out. No part of the function goes out. Well, of course, there are less and less points inside, but the points around the point NL remain always in the function, in this interval and in this quadratic frame. So the limit of the function when v goes to n is L, or when x goes to n is L. This is visible here. The same is here. The only difference is that the function doesn't have a value above L. All values are below L. It doesn't make a difference. We can diminish the frame. We can zoom in as much as we wish to the point NL. And of course, the point NL may not be defined. It can be empty. But as long as we can approach, we can come close to the point NL without hindering, then there is limit. The point NL is not obliged to be defined in the function. There can be a hole, one point, which is a hole here. It can be, no problem. For the limit, it doesn't make a problem. For the continuity of the function, it makes a problem, but for the limit, it doesn't. All right. Here you see, I can diminish the epsilon distance, the vertical distance around L, and I can always find the delta distance. I can always diminish the delta distance around n, so that the points around the function remain in the quadratic frame as well. You see, this is what it means, this definition. And here we have a bigger drawing, better drawing. For the step function, now let's see how the two sort of further functions, the step function and the hyperbola function, they don't have limits. The first two have limits, the second two, they don't have limits. Why? Let's see. If I take my, my sort of looking glass, whatever, this quadratic frame, and make it big, so that I take the whole function, the L1 and L2 in the frame. But I start to diminish the vertically, epsilon. Then I diminish delta, I diminish the frame horizontally as well. I make a zooming in. But if I zoom in this point N L2, after some distance, whenever epsilon is less than the distance between L1 and L2, the difference between L1 and L2, I can find the delta. All right, here there is a delta. I can diminish the frame, but the rightmost part of this function will remain in this quadratic frame, but the leftmost of the function will not remain. One part of the step will remain, the other part of the step will remain outside the frame. So here this function doesn't have a limit, because not all the x's around n remain in the box, in the frame, when I diminish epsilon less than the distance between L1 and L2. You see, this is how the limit doesn't exist. Another way that the limit doesn't exist is when the limit goes to infinity, when the function goes to infinity, when the limit is infinity. And here, let alone choosing it small, I can choose a very big epsilon. I can choose a very big frame, very big quadratic frame. But the part when one side of the function consists of two sides, two parts of the hyperbola. One part will remain, all right, one part will remain in the in the quadratic frame, but the other part will stay outside. I can choose a very big one, but after some point, when I diminish epsilon a little bit, after some point, this the other half of the function will remain outside the frame. So I cannot find for any epsilon which they give to me, I cannot find always a delta such that n minus delta, L plus delta, the image of this these x's between n minus delta and plus delta remain in the distance of L plus epsilon, L minus epsilon, L plus epsilon. So one part of the function remains outside the quadratic frame, so there is no limit either here. You see, that's the point. The values of the function at the for instance left hand side of this asymptote of this axis, they remain outside the frame. So this function doesn't have a limit, it goes to infinity. You see? All right. So let's come to this mumble jumble. Here we have a proof and a counter proof, a counter example. But unfortunately, the presentation has shifted very much when transferred to this program, to our program here. At the PowerPoint slides, it is correct. So what does it mean? If we express all these in terms of an example, for instance, well, in terms of the mathematical symbols, that means what we told now can be told as when the primitive function is y is equal to fx, when x goes to x0 or n, when v goes to n, or x goes to x0 or n, whatever you wish, for all epsilon, for any epsilon greater than 0, there is delta greater than 0 such that when x belongs to the open interval x0 delta, which is x0 minus delta, x0 plus delta, the open interval, y equals f of x, the function values of x, belong to the open interval, to open ball L epsilon, meaning L minus epsilon, L plus epsilon. If this is true, then limit of fx when x goes to n or x0 is L. X goes to x0, but x is never equal to x0. It goes to L to x0. It doesn't go to. It is not equal to x0. It goes to x0. It approaches x0. It becomes closer and closer, but it's never equal to x0. So limit of fx is equal to L. This is the way of mathematical way of writing what we said. This definition we said it can be written like this in mathematics. All right. An example. Q is equal to 1 minus v square over 1 minus v. The example we have seen before. So in this example, what do we do? When v is not equal to 1, we can simplify. 1 minus v square, 1 plus v times 1 minus v. And the denominator we have 1 minus v, 1 minus v, and 1 minus v simplifies. We obtain 1 plus v. The function is equal to 1 plus v whenever v is not equal to 1. What is the limit of q of the function when v goes to 1? Is it equal to 2? We have found it equal to 2. Let's prove that it's really 2, or let's check that it's really 2 by this definition, by this neighborhood definition of the limit. So q equals gv, this function, v goes to 1. For all epsilon greater than 0, or as it tells in the book, for all a1, a2 greater than 0. Instead of epsilon, the book uses a1 and a2, an asymmetric interval. Is there delta? Can we find delta? Is there delta? You see, in mathematics, it's expressed like this with this inverse a, e, with a interrogation sign, which means interrogation mark, which means is there. Only the inverse e is there is. When we put an interrogation mark, it means is there. Is there delta greater than 0? Or as the book says, is there b1, b2 greater than 0? So that for v in the open ball 1 delta, or in the interval 1 minus delta, 1 plus delta, v being in this interval, or as it says in the book, v belonging to 1 minus beta 1, b1 minus b2. Does q remain in the open ball 2 epsilon, or does q remain in 2 minus epsilon, 2 plus epsilon? Or as the book says, does q belong to the interval 2 minus a1, 2 plus a2? If it's so, then limit gv when v goes to n is 2. V goes to 1 is 2. That's what one says. So let's see if this is true. We should check it. Q, the function, should be between 2 minus a1, 2 plus a2. 2 minus a1 less than q minus less than q2 plus a2. Great. If so, and if v is not equal to 1, v is never equal to 1, it approaches 1, but it is never equal to 1, then we can simplify and we can use the function as 1 plus v. It means if q is between 2 minus a1, 2 plus a2, then we can say 1 plus v is between 2 minus a1, 2 plus a2. Or if you wish, 2 minus epsilon, 2 plus epsilon as well. In mathematics, in mathematics books, it would be like this. It's the same. But the book our book uses an asymmetric interval. It doesn't make a big difference. So if this is so, let me try to leave V alone. How shall I do it? I can subtract 1, or I can add -1 to all parts of this inequality. So 2 minus 1 is 1, minus a, 1 minus a1. 1 plus v minus 1 is 1 minus 1 is 0, so v. And 2 plus a2 minus 1 is 1 plus a2. So we obtain 1 minus a1 less than v minus less than 1 minus 1 plus a2. 1 minus a1 less than v less than 1 plus a2. So if q has to remain between 2 minus a1 and 2 plus a2, v should remain between 1 minus a1 and 1 plus a2. But then choose b1 equals a1 and b2 equals a2. So if I replace a1 by b1 and a2 by b2, I obtain 1 minus b1 less than v less than 1 plus b2, v not being equal to 1. What does it mean? For all a1, a2, any a1, a2, however small they might be, I choose b1 equal a1 and b2 equals a2. So I obtain deltas. b1 and b2 are deltas. a1 and a2 are epsilon. So I obtain deltas. There are deltas. There are b1 and b2 for all a1 and a2 for all epsilons, such that whenever v is between 1 minus b1, 1 plus b2, the function values of them, 1 plus v, is between 2 minus a1, 2 plus a2, or 2 minus epsilon, 2 plus epsilon. So the condition is fulfilled, which means when v goes to 1, the limit of this function is really 2. In the counterexample, we will make another thing. We will say, all right, let's assume that when v goes to 1, the limit of this function is 3, not 2. We make a mistake. We just mistakenly, we take this limit as 3. Let's show that this results in an incoherence, in an absurdity. So, if the limit is 3, the function should remain between 3 minus a1, 3 plus a2, or 3 minus epsilon, 3 plus epsilon. I can write down, since v is different from 1, I can take the function as 1 plus v. So 1 plus v must be between 3 minus a1, 3 plus a2. 3 minus a1 less than 1 plus v, less than 3 plus a2. And when I subtract 1 from all sides, I obtain 2 minus a1 less than v less than 2 plus a2. Great. But now, what b1 and b2 shall I choose? I can choose b1 as a1 minus 1 and b2 as a2 plus 1. If I replace them, then if b1 is a1 plus 1, a1 is b1 plus 1. And if b2 is a2 plus 1, a2 is b2 minus 1. So here I replace a1 by b1 plus 1, and here a2 by b2 minus 1. What do I obtain? 2 minus b1 plus 1 is 2 minus b1 minus 1. So 1 minus b1 less than v less than 1 plus b2. All right, that's great. But if I choose, for instance, for any a1, a2, it says. So if I choose a1 and a2 as 0.1, if they give me a1 and a2 as 0.1. What is b1 and b2? a1 is 0.1. 0.1 minus 1 is 0. A1 0.1 minus 1 is minus 0.99. No, 0.9, I mean. And what is B2, A2 0.1 plus 1 is 1 plus 1, 1, comma 1. But if 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 I choose 3, like, well, how can I say, I've taken 3 mistakenly, 3 as my candidate for limit. 3 minus 0.1 is 2.9. 3 plus 0.2 A2 0.1 is 3 3.1. If I subtract 1 from these, I remain with the interval 2 minus A1, 2 plus A2, 1, 1,9 and 2,1, or 1.9 and 2 plus 2.1. But just note that 1 does not belong to this interval. 1 is outside the interval 1.9, 2.1. So when v goes to 1, limit q cannot be equal to 3. You see, v or x doesn't remain in this interval. So this is a counterexample, you see. All right, I understand that all this is difficult at the first glance when you learn for the first time, but you should go over all these, the presentations, the records, and the book, and try to solve the problems by yourself and ask me if you don't understand anything. You can always reach me by my phone, by my WhatsApp, or from by my email, whatever, and ask me whenever you don't understand anything. And here at the end of this chapter, this sub-chapter, let's call it, we have these exercises. Try to solve them as well. Of course, the numeric examples are easier to solve, but these proofs, these delta epsilon neighborhoods are difficult to understand. I accept it, I understand it, but you should try your best to understand them as well. So our lecture is so much for today. I wish you good luck, and well, see you or hear from you next week. You can always reach me through my phone, my email, my WhatsApp, whatever you wish. So good luck and have a nice week. I just stopped the recording.